Let's now start looking at how to design these reactors. When we say design a reactor, it typically means we are trying to determine the geometry of that reactor. In other words, how big should that reactor be? What must the flow rate through the reactor be? And we are usually doing that in the face of some specification. So we know that we want our process to deliver perhaps 50 tons per day. We want to produce a flow rate that, or a stream that has a certain purity of our product. And so we have some specifications that we want to satisfy or fulfill. And we have to do that against the backdrop of nature, and that nature is going to react our species at a given rate. So given the rate that nature is going to operate at, and given the specifications we want to accomplish, there's a specific reactor that we are going to design. In the last notes, we started talking about the fact that among these reactor types, the CSTR, the PFR, and the batch reactor, there was a difference that we observed in terms of the conversion that we accomplished. So given the same residence times, we saw that the CSTR gave us a rather low conversion, or a low overall production rate, and we speculated on some reasons as to why that was. So in this session, we are going to look at explicitly the reasons for this, and these are important considerations for developing our design. And so along with figuring out how to design the reactor in the face of those considerations, we will also be looking at how to design around those considerations. So yes, the CSTR is a bad user of its reaction space or its reactor volume, but is there a way for us to modify the way that we use these CSTRs? Is there a way that we can still make good use of them? So all these are nice design type questions, so let's get into it. We start first with just reminding ourselves about our material balances. So we had for the batch reactor rate of change with time given by this, and for the CSTR and for the plug flow, those were our basic material balances. Now in none of these can we see a nice design parameter. In other words, we would like to find the volume of the reactor. So for the time being, let's let our design question be simply that. We want to know what conversion is accomplished for what volume. So our design question is, what's the volume of reactor required to accomplish a specific conversion? In the case of the batch reactor, let's see how we can translate that to a volume. So first off, we'll just rewrite this equation in terms of our reference component A. So remember, we said through the mole balance, we could relate any component in that reactor to our basis component, whatever that might be. And so it's enough for us to be able to solve this equation in terms of component A, and then we can find all the other species using our mole balances. So we're just going to change the form of this equation slightly. Here we had developed that we were dividing by the concentration, and of course we can rewrite concentration as the ratio of the number of moles and the volume. So in the batch case, that's the basic mass balance. Now we could repose this equation by integrating this. So let's imagine that we multiply dt out here, and then we divide by minus RAV over NA naught. So we've got dt out here and dxa. And by the way, it's not quite right to say it the way I just did. It's not about multiplying by dt. This is not the ratio of dxa to dt. This is an actual operation. We really read this as ddt of xa. So ddt is the operation we perform on xa. So it's not like we are multiplying. We can multiply things out here. But the correct way to think of it is that we are just integrating in time on both sides. So anyway, if we can, of course, divide by this term here. So you can think of it as dxa, and in its denominator, it's going to have RA. Right, so you've got dxa here, and then you have minus RA in the denominator when we divide this, and then we are dividing, so you can say it's times Na naught over V. So Na naught over V is a constant. Those are not varying with XA, so we can take that out here. And so it's just dxa over minus Ra. And then if we integrate on both sides, then in this case the variable is XA. So integrating naught to XA. So here this XA is of course the desired conversion. So from our production specification, there exists a specific conversion we are trying to accomplish. So we know, for instance, we are trying to achieve a 60% conversion in the reactor. And then the XA here, normally we would write XA dashed just to make this variable different to that one. But anyway, for convenience, normally we just leave it like that. So that's what we have on this side if we integrate. And then in terms of time, if we integrate that also, then it's T. So those are the mechanics of how you go from your material balance there into this form. And then going past the mechanics and looking at what this means, we are saying here, if we have a specific reactor volume V, and if we put into that reactor this number of moles, Na naught, then the time it takes to accomplish a conversion of that amount in that volume, the time it takes to get to XA is this value T. So this is the time taken to convert Na naught in reactor volume V to this extent, right? And here our reaction rate, we are just saying here, this is just being specific, right? That Ra is a function of XA. So it's just a little reminder here that yes, Ra is going to be a function of XA. So when we do this integration, we have to respect that. Okay, so that's if we were to repose our material balance in terms of the time taken to accomplish a specific conversion in a specific volume. We can, of course, change this a bit. We can rewrite this instead as the volume required to accomplish a certain conversion within a specific time. So mechanically, it's just a matter of multiplying the V there and dividing the T there. But we read this as that if we want to accomplish conversion XA within time T, then this is the volume that we need for the reactor. So only a reactor of this volume can accomplish that conversion in that time. Right, so that's how we can design the reactor in the batch case. And we notice here that in this design equation, we have this term dxa over minus Ra. So we'll just remember that. We won't do anything with it right now. So that's the batch case. Now let's move on to the CSTR. So looking back at the design equation, that's what we have for the CSTR. We said xi over tau is minus Ri over Ci in, so the inlet concentration there. And then, of course, tau is the definition here, the space-time, which was the volume divided by the volumetric flow rate. And we said nominally that this seems to us like the average time that the fluid spends in that CSTR. And we'll come back to that and show why explicitly that's true. But for now, we'll just say tau is that ratio. So that's our CSTR balance. And now, again, we want to rewrite this in terms of the volume. So it's very easy to do that here. Tau is simply V over Q. We can substitute that there. And then take V to one side and move everything to the everything else to the other side. And rewrite this in terms of component A. So that's all that we do here. So if you just rearrange this equation here, substituting for tau, that's what you get. So again, it's telling us if we want to convert a certain initial concentration by an amount XA, if that's the amount we want to convert, and if that's the volumetric flow rate, and if that's the reaction rate, then that's the volume that we need that CSTR to be. So that's our design. That's how big that reactor needs to be in order to accomplish this conversion. You might wonder, why does volume vary with this? Why do we need... So we can see here as XA increases, we are going to need a bigger volume. And a way to think about that is with our CSTR, we've got a certain flow rate across that CSTR. And the bigger we make that CSTR, the more time that fluid is going to spend there. So imagine a CSTR volume and a flow through that volume. The bigger you make that volume, if you are not changing the flow rate, if you're just changing the volume, the bigger you make that volume, the more time that fluid will spend there. Right, so the more time spent there means there's more time for reaction, and hence you get a higher reaction rate. Okay, and then if you look at this equation, the inlet concentration multiplied with the flow rate, the volumetric flow rate, this product is simply the molar flow rate in. So that's FA in, and the rest is the same. And now again we can see the volume is proportional to an x on the in the numerator, and that's divided by a minus RA. So there's some similarity with our batch case. We said a similar thing in the batch case, right? So in the batch case we had and something to do with x on the top, and then an 1 over RA. So we are seeing a similar thing for the CSTR here. Moving on to the plug flow reactor. So that's our material balance that we derived before. And then we just rewrite that in terms of our reference component A, and we rewrite this tau in terms of volumes and volumetric flow rate. So tau being V over Q, we can write d tau as dV over Q, and so it looks like this. Right, so that's the term here, and then of course we have to integrate this. So again, if you divide both sides by the right hand side here and then integrate with volume, then the volume is going to integrate to just the total V, and then on the other side you are going to get dxa over minus RA, and then you've got QCA in over there. So we need to integrate this again, and then this product, volumetric flow rate times inlet concentration, that's nothing but the inlet molar flow rate. And then this is, again, this thing to do with XA on the top, and then divided by RA minus RA here. So you've got the same term again. And so just to summarize that, you can see here in the batch case, your volume is proportional to dxa here, and then your minus RA there. In the case of the CSTR, again, something to do with XA up here and minus RA down there, and the same thing here for the PFR. And then for CSTR and PFR, you've got FA in, FA in. Here you've got NA naught over tau. And if you think about this, this is the total time spent reacting, right? So this is all the time that was spent going from naught to XA. And you had initially a total NA naught. So in the batch case, you had charged everything in, whereas in the flow cases, you continuously fed A in. So this, if you think about this, this is equivalent to the, if the batch was somehow a flow case, then NA naught over T is in effect the molar flow into the reactor. So in a way, all these equations have very much the same form. So the FA in part, there are some equivalencies we can see among them. Then in terms of the integral here, you've got a dxa, you've got 1 over r integrated in x. So 1 over r integrated in x. It's just that in the case of the CSTR, instead of having 1 over r, you do have a 1 over r, but instead of being integrated in x, it's being multiplied by xa here. Now, we can produce what we call a Levenspiel plot, right? In each case, we can see some relationship between the volume and 1 over RA. So the Levenspiel plot starts out like that. In the Levenspiel plot, we simply go ahead and make that plot. We say 1 over RA plotted against conversion. And if you go ahead and do that for example, a first order reaction, let's just look at what we would get in that case. So if it's a first order reaction, so let's say we have something like minus R sub A equals KCA, then of course we could rewrite that as K times CA naught times 1 minus XA, and we then want to plot minus 1 over RA. So we want to plot that against XA. So in other words, we are plotting 1 over the stuff against XA. So it's an inverse type of relationship here. So minus 1 over that. That's what we are trying to plot, okay? Oops. I'm just going to make this. Right, so we are plotting basically an inverse relationship with XA. So if you do that for a first order reaction, right, and that's what we have here. This is clearly a first order reaction. Your reaction rate is linear with respect to Ca. So remember, normally there's some stoichiometric coefficient power up here. In the case of the first order reaction, that means it's directly proportional and the order is 1. So that's R equals KCA. And so even though it's an easy first order relationship, in our Levenspiel plot, we are plotting 1 over RA. So if you rewrite that in terms of conversion, if you go ahead and plot that, you'll see that that function looks like this. Right, so we have this, this is how it's varying in the first order case. And we can now think about what this curve means in terms of the three forms of for the three reactors. So in the case of the batch reactor, we are looking at the integral of 1 over RA. So we've plotted 1 over RA. Here's the blue line is the curve. And let's say we want to know the volume to get to 60% conversion. So there's 0.6. So this is saying basically, look at the area under the curve, right? This is the integral of minus 1 over RA, which is what we are plotting here. So basically this area 2 is going to be this number. So this factor here is going to be equal to area 2. And that's the same here, right? It's exactly the same function in the sense of the plug flow reactor. So 1 over RA as a function of XA, and we've taken the trouble to go and plot that out. So you always have to go back, look at your form of your rate expression, and then work out how to draw that curve. So we've done that bit of work. We know that's the function. So we've plotted that out. And now we are finding that our volume is proportional to the integral under that curve in these two cases, in the batch and the plug flow case. Right, so their volumes are both proportional to area 2. Now let's look at the CSTR. So the CSTR is saying basically we are taking XA and dividing by minus RA. Another way to say that is it's XA multiplied with 1 over RA. So XA multiplied with 1 over RA. So the easiest way to do that is to look for that XA value. So we know we've specified 60%. We look up here and that tells us what the 1 over RA value is. So there's 1 over RA, close to 0.4. So that height 0.4 and that distance 0.6. So the product of those two, according to this, the product of those two, XA and 1 over RA, the product of those two is proportional to our volume. So that width multiplied by that height, that's basically the area of this. So we just have to find the point So we are given the conversion, we just look up the point there, then that determines for us the height, right? So from the curve we get the height, and then we know the width, we know the conversion. So it's basically the area of this box, which is area 1 plus area 2. And if you think of that, then it's telling us that this CSTR requires a greater volume than the batch or the plug flow case. Remember these two, and you can see it here explicitly, they are simply the area under the curve. So they are only proportional to area 2 here, the area under the curve, whereas the CSTR is this total area here, area 1 plus area 2. So the CSTR requires this additional volume, which is symbolized by area 1. And we said we anticipate that's true because the CSTR is stuck everywhere to the same concentration. Remember, CSTR is perfectly mixed everywhere. And so if you have a specific conversion in that CSTR, so at steady state, you achieve a certain conversion, in this case 60%. So there's a 60% conversion in your CSTR everywhere at all times. And that means you only have component A, your reactant. You only have 40% of component A in that reactor. So you are stuck all the time to one low reaction rate in that CSTR. And that shows up by needing extra volume. So you need a bigger reactor for the CSTR because you've got this because you've got a low concentration, you need to fill that reactor with more material, with more mass. You need more mass in that CSTR because you have in effect a lower concentration in the CSTR. So for a lower concentration, to get the same number of moles of A in, you need a greater volume. So you need more volume to accomplish the same conversion in the CSTR, right, compared with the batch and plug flow reactors. And like we said before, in the batch case, you didn't need such a big volume because there was some time when you had a high conversion. So initially, in the first couple of seconds, your concentration of component A is nice and high. It's not as yet at a high conversion. So initially your conversion is 0 in the batch reactor. So for some time you have a high concentration of component A, and as time goes on, you've got more A converted to your product, and so your concentration goes down and you get lower rates. But at least there was some time, there was a good space of time where you had a high concentration, you had a low conversion, which means you had a high concentration of A, and so you needed only a small volume for those times. A similar thing in the plug flow reactor. It's flowing across this tube, and near the front of that tube, you've got a high concentration of component A, and as you looked further down the tube, you saw lower concentrations, but at least you had a space where you had a high concentration and hence a high rate. So that's why in both these cases, I need your consent. In both these cases, we need less volume. In the CSTR, both in time and space, you are losing out, right? The CSTR, we are thinking of that as being at steady state. So it's stuck to the same operation in time always. And in terms of space, it's got the same concentration across its space everywhere. So in both cases, it's lost out. It's stuck to the same low reaction rate, right? So in time, there is no other time to think about. There's one steady state for the CSTR. In the batch, at least you have multiple times, right? Things are changing in time. So it had some initial time when it had a high concentration. In the case of the plug flow, so it's the CSTR across its space, it's the same concentration everywhere. In the plug flow, that's not true. In plug flow, your concentration is varying axially down the tube. So in plug flow, near the front end of that reactor, you had a high concentration. So in that zone, you needed less volume to accomplish the same conversion. So that's why the CSTR requires this extra volume here. There's no way for it to have a high concentration region or time, and so that shows up there. However, if we think about it, The CSTR is in a way the easiest reactor to create, right? The CSTR is nothing but a vessel with a stirrer in it, at least conceptually, right? Remember, these are all ideal reactors. CSTR, we are thinking, is infinitely fast mixing. So in the real world, we can't accomplish infinitely fast mixing without infinite amounts of energy, but still we can approximate its behavior. It's fairly easy for us to construct a CSTR. We create a pot, we put in a good mixing, and we get close to CSTR-like behavior. So it's easy to do this in the real world. In the batch case, you can easily create a batch reactor in the same sense of a CSTR. So a batch reactor is perfectly mixed, and you can seal off any flow from happening. So you can construct a batch reactor. But we know that the batch reactor suffers from other disadvantages. So in the batch reactor, it's continuously disrupted behavior. So you have to charge that reactor with Na0. You have to wait a specific amount of time, and then you stop the reactor, you open it up, you remove your product. You may have to do additional work on that reactor to get it back to its original state, and then you charge it again, and you restart the whole reactor. So if it's 5 hours of reaction time, there might be an extra 2 hours. So the batch reactor, it suffers from this disadvantage that it's interrupted operation, all the time interrupted. You batch your reaction, and then you have to recharge the reactor and restart the whole thing. So there are real practical disadvantages to the batch case. In the plug flow case, it's a different problem. We require that all the fluid flows in a perfect plug, that no plug of fluid, no element of fluid mixes with any other element of fluid. And that's virtually impossible to accomplish, right? So in your plug case, you are requiring that your wall friction doesn't cause laminar flow, or even if there's perfect turbulence, that turbulence doesn't happen laterally. You are requiring that there's no diffusion, or more generally dispersion. So you can't allow any axial movement, otherwise you don't have plug flow anymore. So yes, these two look nice, but they are hard to accomplish, and they can be impractical. Although you do get batch operations for pharmaceuticals and so on, but for general chemical engineering, we don't want batch operation. We want to move to continuous operation. So these two have what looks like good volume use, but they are almost impossible to do here, or they have practical disadvantages. Right, so those are some of the considerations, and we are looking in this session at how to design our way around this. There's an example here where you've got components A and B being converted to C. So please work through this, work out what volume is required to accomplish the specified conversion of 75% here. So I'll leave you to do that. Let's move on to the extensions now. So we've just introduced this Levenspiel plot, and we can see there's a way for us to estimate the required reactor volume. And let's see now how we can use this method to optimize our reactor. Let's get creative with our reactor design, and let's consider some possibilities. Well, first off, let's just think about the case of reaction inhibition. So in the case of inhibition, your reactant might cause your overall reaction rate to slow down. And that actually does happen in some biological systems. So in biosystems, where you are usually trying to keep your microbes operational, sometimes if you overfeed the microbes with substrate, then that can actually inhibit their growth or even stunt their growth. So there are reactions that have this strange behavior, right, where your reaction rate is actually inversely proportional to the concentration of your reactant. It's not really usual. It's not a normal thing to observe. Most reactions don't look like this. But in the specific case where your reaction rate is going down with your concentration, then you do have, if you plot 1 over RA against X, then you have this form. Now, this then would be a case where the CSTR actually has an advantage. So let's say you've got your 60% conversion, and then we said for the PFR and the batch reactor, the area under the Levenspiel curve is proportional to the volume. And here you can see the area under this curve is actually more than the area for the CSTR. So the CSTR is just the 1 over R value multiplied by the conversion itself. So the 1 over R value times the conversion, that's proportional to the volume. So in this kind of strange case, your CSTR can do better than the PFR and the batch reactor. So that's just a kind of an interesting case. It doesn't happen that often, but it starts to show us that when we can look at things graphically like this, there might be other possibilities that occur to us. So let's think then, what if we have something like this? What if our reaction kinetics were strange enough, right, that when we went through this exercise, right, we specified our reaction kinetics here, we substituted our rate expression, we did our mole balance, and we converted that concentration to a conversion, and then we plotted 1 over the reaction rate versus XA. So you've done all that work, and now you find this weird curve here. And I'd like you to actually pause the video and think about how you would accomplish the lowest possible volume in this case. So I'm not saying this is a first order reaction. It's clearly not first order. It's some weird reaction rate expression. And there are definitely, we will definitely encounter those in practice. There are many weird rate expressions we come across. So anyway, we've got some weird rate expression that led us to this Levenspiel plot. Now, can you propose a way to get the smallest possible reactor volume? Right, and the overall goal, we want low reactor volumes because that leads to lower costs of fabrication and operation and all that. But anyway, here, let's say this was our desired conversion. So we would like to achieve a conversion somewhere here. So how would we, what choices would we make to reduce that volume? So pause the video, think about that, and then let's have a look at the solution. Right, so let's look at the solution here. Now, in this part of the curve, again, we have this kind of inverse slope, and so we could say, well, in this region, while the curve is sloping like this, if we use a PFR, then it's going to be, or a PFR or a batch reactor, we are going to require a volume that's proportional to all this area. Whereas if we use a CSTR up till this point, let's say we can operate a CSTR to this conversion, we can see we'll get a very low volume CSTR here. Right, if we try to go further and if we try to use a CSTR here, then of course we are going to get all that wasted volume there. But let's say we use 2 reactors, and let's say we operate just at this point. So you've got a nice low volume of your CSTR here. So it's going to be much lower than the volume of a PFR, which will have all this, which will be proportional to all of this. So our CSTR will only have that volume, so that's our CSTR there. And then, of course, our final required conversion is somewhere out here. And so out here, it wouldn't make sense to use a CSTR because going up here, you'll have all that wasted volume. So after this point, we would then use a PFR or a batch reactor, probably a PFR because we want continuous operation. Right, so that's the solution. We partition our reactors, we make 2 reactors of different type, and we figure out from our kinetics, from what nature tells us, from our measurements about nature, we figure out from the kinetics where that minimum point for conversion is, and then we design our CSTR up to that specific conversion. So using XA, we can work out the volume of the CSTR, and then we put that in series with the PFR. And so those two together will give us the minimum possible volume to accomplish some overall conversion here. Right, so that's how we can navigate this Levenspiel plot. So that's how we think of these plots. We want to navigate it, and we navigate it by designing our reactor system. And we are allowed to propose networks of reactors, and so that's how we can combine our knowledge about reaction kinetics and what nature tends to do, and how we as reactor designers can navigate that plane and accomplish and meet our specifications. So that's if you had that weird set of kinetics. And then further to specifications or further to tools that we can use in our design, we also define this Darmkuhle number. So the let's do some development before we define it. So we know the CSTR design equation. We can rewrite it like this. So just multiplying by tau and dividing by this thing. That's tau. And if it's a first order reaction, we know we can replace this minus RA by a KCA. And then that CA we can rewrite as CA in times 1 minus XA. And then, of course, the CA ins can cancel, leaving us with XA over K times 1 minus XA. And then if you, right, so we can multiply the K out here. So we can say K tau equals this stuff, XA over 1 minus XA. And then, of course, you can multiply out 1 minus XA and group out XA. And you can show that you can rewrite the same equation in this form. So you can write XA equals K tau over 1 plus K tau. And by the way, if you think about this, this equation makes perfect sense, because if you think of K tau, that's in effect the amount of reaction that's happening. So K is proportional to the rate of reaction, and tau is the average time spent in the reactor. So the rate of reaction, a number that's related to the rate of reaction multiplied by the time spent reacting, that's in effect how much reaction is going to happen, and then divided by that. Now, if you have a very low amount of this here, let's say the reaction was very, very slow, so K was close to 0, or let's say it was a very tiny reactor, so tau was very small. So this amount, if it's very small, then not much reaction can happen, and so we expect the conversion to be very low. So if K tau tends to 0, you've got 0 over 1 plus 0, which is 0 over 1, which is 0. So yes, it agrees with what we expect. We get low conversion for low values of K tau. And then if K tau is very large, right? If you have an extremely fast reaction, so K is a large number, or if you have a massive reactor with a slow flow rate through it, right? Then your average time there is very large. So if this product is a very large number, then you can say in the denominator 1 plus K tau is going to be approximately K tau. In other words, K tau is much more than 1. So the denominator approximates to K tau. So it's K tau over K tau, and that's a 1. So if you have a large K tau, that goes close to 1. So for a low extent of reaction, you get a low conversion. For a high extent of reaction, you get high conversion. So specifically in the first order case, you find this form, and then we propose for first order, that's we define the Darmkuhle number, so DA1, right? So that 1 tells us it's first order reaction. Okay, so the Darmkuhle number, you can see is K tau in that case. If it's a second order reaction, you can follow the same steps, right? In the second order case, your reaction rate minus RA is KCA squared. So you'll have here Ca in squared 1 minus Xa squared. So the Ca in here can cancel with the square there, and excuse me, you'll have left over here a Ca in, and this will be 1 minus Xa squared. And so well, that's shown here, right? So that's what you'll have, and so if you solve this equation or rewrite it, well, yeah, in terms of Xa, you can see this is going to be a quadratic equation, so you can solve it in terms of Xa here. And in this case, you define the Darmkuhler number differently. So you'll, if you work through the algebra here, you'll find that the Darmkuhler number will in this case be Kca in times tau. So if you make that substitution, you'll find that you get that relationship. So again, Kca in times tau, that tells us the extent of the reaction. And so that's Darmkuhler 2. And in this case, again, if you apply a Darmkuhler close to 0, then you are going to get a number here. You can see if it's close to 0, then this number tends to 0. And if it goes extremely large, then this number gets closer and closer to 1. So you can see as it gets closer to 0, then you're getting 1 minus 1 here. And then divided, so that's effectively a 0 divided by another number, so that's close to 0. But anyway, so if it goes faster to 0 up here than down here, that goes closer to 0. So so for low values of Darmkuhler, you get low values of Xa, and for high values of Darmkuhler, then it's much greater than the 1, and then you'll have here the square root, that basically this is going to cancel there, leaving us with a 1. Right, so generally speaking, you can define the Darmkuhler number for any order of reaction, and so you'll need to look up the specific form for the order of reaction, and then you'll be able to say generally that for a low value of the Darmkuhler number, your conversion is low, and for a high value, it's high. Right, so that's just another useful thing that's often used in reaction engineering, just for your awareness. We actually won't use this right now. Anyway, so I guess that was just a little break from the design parts. So coming back to CSTRs in series, so here we had introduced this notion that we could break up our, we could create a design that basically broke up our conversions. So we know we want one final conversion here, but it's not the case that we only need one reactor, or that we are only allowed to use one reactor. So quite often we will use multiple reactors to accomplish some desired overall conversion. And that's our creativity, right? That's it's up to us to say how this is going to happen. So the financial people might say, yes, I want so many tons per day, and then we work out that means that we need this amount of conversion. But there's nobody to tell us, well, and you must only do that with one CSTR or something like that. So it's up to us to figure out how to get to that overall conversion. So we can think about all kinds of other options. And another one is to consider CSTRs in series. So you have your original feed here, and we know we want a specific concentration out here. And we may choose to do that with multiple reactors. In this case, we could use 3 CSTRs in series. And you can see here that as you use more CSTRs, you are getting further away from this problem of wasted volume. You can see here, if this was 1 PFR, then you would have a lower volume, right? You need less volume for the PFR, so you wouldn't require all these extra little volume pieces. But still, it's much better than having just one CSTR. If you had one CSTR for this X3, then all the space above the curve would be a wasted volume. So as you use more CSTRs, you can see you are getting closer to this curve here. And in fact, we'll come back a little later to the case where you have an infinite number of CSTRs in series. So anyway, for now, just saying that there's some reasonably small number of CSTRs. Let's look at how we can modify our expressions to determine the conversion that we accomplish. So we've just shown just now through that Darmkühler discussion, we've shown that the conversion when given K tau for a first order reaction, it looks like this. So in the first reactor, or coming out of the first reactor, that's going to be the conversion. So that's our X1. So if we happen to know the volumetric flow rate here and the volume there, then we can calculate tau, and then from the reaction kinetics we've got K1. So knowing those two, we can work out where we are going to end up here. So we'll say, okay, from the first reactor, because it's that volume and that flow rate, that's going to be my first conversion, X1. Then you would say, well, then going into the second reactor, we can say that the amount coming in, it's no longer FA0, it's now FA1, which we know, right? We've worked out what the concentration is here. So we've got the conversion and we've got the entry concentration. So just X times Ca0 equals Ca1, and we can multiply that by the volumetric flow rate and say that's my molar flow rate going into the second one. So we've got that as a number, and then we don't as yet know this one, or maybe so maybe we know the volume here, and so anyway, we can say we know this part of it, and then or if we specified, let's say we said from our second reactor we want a further conversion, so maybe we managed to do 20% conversion here, and then we did another 20% conversion here, then we can say, well, then of the concentration coming here, I want to convert a further 20%. So that then tells me what Ca2 will be. So I've got Ca1 and Ca2, and then you do this calculation, and that will tell you the volume of this part of that train. So you've got the volume there. And then you can do that yet again. You can work out the volume going in, the molar flow rate going into the third reactor. You can say perhaps I need another 20% conversion here, and then you can just apply a Ca3, and you can work out the volume of the third tank as well. You can see they are getting bigger and bigger. So as you convert more of A, your concentration of A is going down. That means your reaction rate is going down. So the reaction rate here is much lower than the reaction rate here. And so you need bigger volumes to accomplish the same change in conversion. Right? It also answers the question, how is it that just by making such a simple change that we can accomplish a smaller volume? So if you had just one big reactor here, maybe that would be 50 cubic meters. And then if you replace that by 2 CSTRs in series, it might be 5 here and 10 there. So let's say it was 2 CSTRs in series. You might find you need 5 cubic meters here and 10 cubic meters here. So 15 cubic meters instead of 50 cubic meters for just one CSTR. And that looks like magic, right? You're wondering, why is it that just by creating a partition in this one reactor, so taking that one big reactor, if I just make a small partition of that reactor, if I just split it up, just the simple act of splitting up that one reactor, how is it that I then need even less than when I add the two together? Right, so if you add these two volumes together, the total amount is still less than the volume you need for the one reactor. And that's simply because in this reactor, you now have a zone with a high reaction rate, higher than you'll ever get in here or in the big reactor. So you've now created one highly efficient space, right? Because you've got a low conversion here. You are maintaining a space with a nice high concentration of A, and so that's how you are able to save so much volume. So sometimes the sum of the parts is actually, I don't want to say more than, so I can say better than. Sometimes by adding up the contributions from the parts, their total contribution is more than the contribution of one thing by itself. Right, so that's what's happening. We are maintaining one high efficiency zone, and so that overall improves our performance. But the point of this page is more about how you do the calculation. So, given that you've got multiple reactors together, you can calculate the volume needed for each one like this. Okay, so that's now looking at each reactor in the train. Now we can take a step back and say, yes, if I look at this equation, for instance, I can go ahead and divide here. So V2 over Q, I can call that a tau 2. So I can say tau 2 equals the stuff, and then let's multiply this denominator by that, and then group out for Ca2. So if you do that, and please do these mechanics yourself, you'll find this form. It's Ca2 equals Ca1 over 1 plus K2 tau 2. And now Ca1, we do have an expression for this. Right? We know that Ca1 equals Ca in over 1 plus K2 tau 2. Right? So you substitute for Ca1 here and you get this form. And you can start to see a pattern emerging here. So as you look further down the train, so you had Ca1, we are looking at Ca2, let's say we had Ca3, then you would anticipate that Ca3 would be this divided by this times 1 plus K3 tau 3. And so generally you can say for n identical CSTRs in series, you can get the concentration coming out of the nth reactor simply as Ca in divided by 1 plus K tau raised to the power n. And if you look at this, you can say, well, I can estimate my conversion quite easily. I can say Ca in minus Ca n over Ca in. You can see that's going to be this form. So I'm skipping through a couple of steps here. Please do these back of the envelope verifications of the algebra. But basically, you can easily estimate the concentration at any stage in the train of these reactors. And so you can write your balances and estimate your conversions at any stage here. So that's the case of CSTRs in series. So I guess we've talked about this. As you do this, you are able to get lower volumes, and as you increase your number of reactors, you are getting a much more efficient operation. And so we are starting to get the best of both worlds now. We said CSTRs are nice and easy to construct. You just need a pot and a stirrer, so enough agitation, and then you are able to start that reaction. But we also said that's also giving us the worst use of the volume. We are seeing now that as we partition the one big CSTR into multiple CSTRs, we are also getting closer to the ideal behavior. So PFRs and batch reactors, those all have disadvantages, right? But with the CSTR and its advantage of simplicity, we are still able to start to get better operation. The concern, however, is with the CSTR, you can't keep doing this. So your 150 cubic meter reactor, we know we can get it down the absolute minimum. If we break it down into tiny reactors, we can eventually get under this curve. Not under the curve, but we are getting closer to being on the curve. But to really get that close to the curve, we then need many tiny CSTRs. And you see, each time you add another CSTR to your train, you are increasing the overall cost of the system. So yes, you are reducing the overall volume of the reactor space, but each reactor comes with its own costs. So there are overhead costs to each reactor. So you need to do your heating and cooling to each one. You need to implement control systems. You need to fabricate each one. So the capital costs of each reactor is a factor that's going to lead us to say, I can't keep doing this. I can't forever keep breaking down my volumes into tinier and tinier sizes. So it's not possible to keep doing this. All right, so those are the things to think about, and we do have to then optimize the number. So N here, the number of CSTRs that we use. We do have to choose that carefully, and really it's a matter of then optimizing the cost of setting up this train of reactors. So we will find an optimal number. So maybe it's 3 or 4 or 5 CSTRs. So it gives us a nice low volume, but at the same time, the overhead costs are not so high that we can't even construct it. So we carefully optimize N, and then we get the best of both worlds. Easy to create reactor, and still fairly efficient. So that's CSTRs in series. And this was the case where we are considering equal conversions. So like we just showed, in the case where we choose an equal conversion in each reactor, it's very clear and easy how to do this. So if it's 60% and we choose 20, 20, 20, then that defines for us the concentration at each stage. And we can use that, as we said, in our design equations. If we know it's 20% conversion, that easily defines then the second concentration and the third concentration and so on. So it's very easy to work out the volumes in this case. However, it's not normally that we would like to have these different types of volumes, right? It's not usually the case that if we are going to produce 3 reactors, that we say to the manufacturer, okay, make this one 5 cubic meters, then I want the second one to be 7.342, and then the last one, I need that to be 13.579. So we don't normally have in our reactor designs that amount of variation in our unit geometry. So we would like our units to have similar volumes to each other, and that tends to make it easier in terms of maintenance and so on. So if you have similar sized reactors, then that means their wall thicknesses can be equal, and that means there are lots of other important things like you can have the same spares available for all the reactors and so on. So many practical considerations become possible when you look at equal volumes instead. But we can see here equal volumes are never going to give us equal conversions. So let's look now at case 2, where the volume of each stage is known and possibly equal. Well, in this case, VI, so the volume of a specific stage, is defined, and then we can think about our design equation. Excuse me. So this is nothing but our material balance, right? And thinking about the ith stage in the train, that there's going to be a certain molar flow into the ith stage, which is FA in times XAI, and then coming out of the ith stage is that one. So sorry, this is what's going in, and then that's what's coming out. So this higher conversion is what's coming out of the ith stage, and then this one is what's going in. So that difference is the number of moles, the molar flow rate, and then divided by that tells us the volume of that ith stage. So go back to your material balance and verify that you agree with this. So anyway, you can rewrite this equation in this form. So if you just take your reaction rate out here and then you divide by the volume there, it looks like this. And if you think about this, then it's simply saying that if we know what conversion, or not we know what conversion, if we know a current conversion and we know a gradient, then we can step forward along a line. So if we know currently we are here, right? So let's say we start with the first one. We know our current conversion is 0. And then if you look at this relationship between R, A, and X, right, it has this factor in front of it. So that's in effect the gradient. So there exists a line along whose gradient we are moving as we reach the next conversion. So we move along this line until we reach the desired reaction rate. So that's there, and then that tells us what the conversion is. So once more, we work out the slope, right? The slope is simply FA in over VI. So you move along the slope until you meet the reaction rate. So when you are equal to the reaction rate, then that defines the conversion in that reactor. So looking at this equation, you are allowing the conversion to vary if you like, and then there will come a time when this equals the reaction rate. So you vary this, and you can see the relationship between your y-axis and your x-axis, so R, A, and X. The relationship between those is this factor out here. So that's basically the slope, or if you like, dRA dx is equal to FA over VI. So that's the slope of the line. So you are moving along this line, and then when this line meets RA, when the value equals RA, then we know we've reached the conversion for that reactor. And that's all we need to do. We just move along the slope, we meet the line, and then that tells us the conversion in that reactor. And then for the next reactor, we say, well, we have x1, we want to know x2, and for that next reactor, FA in that's in terms of the overall train of reactors, and then we know the volume of the second tank. So for example, we might have specified all the volumes must be equal, or we are using a specific set of vessels that we already have. So we know this volume, right? So case 2 is where we know the volumes. Case 1 was we knew the conversions. So case 2, we know the volumes, we don't know the conversions. So in the second reactor, we know this ratio, we have volume, and we know the total flow in. So that defines again the gradient, and we have the starting point, right? The conversion from the first tank. So we use this new slope, and then we move up until we meet RA. So that's when these things are equal. So it's equal to RA here. Then that defines for us the second conversion. So we keep doing that. However many reactors we have, we just we use the right. We look at the volume, and then we take that ratio, and that tells us the slope. And so we use the slope, and where that hits RA, then that tells us the conversion. So it's as easy as that. So if you want to do it graphically, you don't really need to do it graphically. You can just use this equation. Note that this is not the Levenspiel plot anymore, right? We are just using RA directly here. So anyway, that's how you do it in case 2. So you know the volume of each stage, and you don't know, well, I wouldn't say overall conversion. You can say you just keep adding those known volumes until you reach an overall conversion. But you don't know the conversion of each stage. So we should probably update this to say stage conversion unknown. So that's case 2. That's how we do that. Pretty straightforward. And then case 3, right? So the two cases we talked about now are kind of arbitrary. Right? If you look at case 1, we just arbitrarily said, oh, we want 60% here, let's just use 3, so it's 20, 20, 20. So that's a completely arbitrary. There's no real reason for us to choose 20, 20, 20 like that. In this case also, claiming that we know the volume in each case, or saying that the volume. So we gave a couple of practical reasons for keeping the same volume, and that's fine. But at this stage in our reactor design, we don't have to be so practical, right? We still like to try to be clever, right? We'd still like to say, can't I think of the right way to do this? What is the best way for me to create a really clever reactor design that's going to operate really well, that's going to give me the absolute best possible performance, which is going to cost the absolute least amount to construct and operate? And so we could say instead, the most interesting case we can think of is, what's the absolute minimum volume that we could get away with? So we've defined some overall conversion, x2 here, 60%, let's say, or we've been saying. So how do we choose the volume of the first reactor such that the total volume is the absolute smallest possible amount it could be, right? And we can actually take advantage of some geometry to answer this. So once more, let's just define the problem. We know the final conversion that we want, and let's say for now we are talking about doing that with just 2 reactors. Now we could just choose equal conversions. So we could say x2 divided by 2. But we know if we do that, we are not guaranteed that that's the best possible choice. So there's no guarantee that just choosing x2 equals half, x1 equals half x2. There's no guarantee that that's going to give us the smallest total volume of CSTR. And secondly, if we just specify volumes for x1 and x2, and we operate like in case 2, then there's no guarantee that those were the best choices. So we are trying to be a bit cleverer now and think about how we can actually minimize the total volume of this overall train of reactors. Okay, so let's think about how to choose our reactors in terms of this picture. So remember our Levenspiel plot, we are plotting -1 over RA against X. And let's say we are doing this for just 2 reactors, and we are prescribed our final conversion. So we are told we want overall 60% conversion. So that's fixed. So the final conversion x2 is fixed, but we are free to choose how big to make each of these 2 reactors. So if reactor 1 is chosen poorly, then you'll have a large overall volume. And we can think about what happens as we slide this x1 value around. So remember, as we choose different values for x1, that's going to determine the total volume. So let's say we've chosen x1 here, then that fixes for us that this is the point x1 is operating at, and hence this is the volume of the first reactor. And then, of course, we still have to do a second reactor, and in that second reactor, we have to get to x2. So this is then the volume that we have to accomplish in the second reactor, or that's the volume we have to build to get to that required final conversion. So as we choose different values for x1, that changes the total volume of the system. Now we could choose an x1 value right down here. Let's say we chose x1 to be 0. In other words, we made a reactor that was so small that it did nothing for us for the conversion. So if we did that, then that means we have to accomplish all our conversion in the second reactor, and that means our total volume is going to be this big block here, and that means we have all that extra volume that we don't need in a CSTR and so on. So that's one case. Then if instead of at 0, if we shifted x1 all the way across here, then that means the second reactor is 0 in volume. And then again, you have one big reactor that's doing all the work. And then if you move x1 to some intermediate value, you can see that you get a lower volume. So you no longer have this whole big block. You now have saved this amount of volume. So you can see that as you slide x1 along here, you are changing this area. And so the bigger we can make this area, the better our overall volume will be, the lower our overall volume will be. So you could say that our choice of x1 translates to what what choice here is going to give us the biggest area there, right? So that's the basis on which we optimize x1 value. And if you take your basic geometry and let's say we have some arbitrary curve. So here I'm not talking about a Levenspiel plot or anything like that. I'm just saying, let's say we have some function y of x, and then if we look at this area y times x, so we choose a specific x value, and then that determines for us a specific y value. Then the area for that point, right, y times x, is that one. And so the area here is, of course, x times y. And then if we want to maximize this area, we can differentiate this. So we can say dA equals y dx plus x dy. All right, so from your basic calculus, you can differentiate that area and say, well, we would like to maximize this area. So dA equals 0. So there exists some turning point that maximizes. There's some choice of x here, which will give us the maximum area here. And again, of course, if you move x too far here, then you'll get a 0 area. If you make x too small and it's sitting right here, then again you get a 0 area. So there's some intermediate value of x that gives us a nice area, a maximal area. So we are differentiating in 0 to get that. So if you differentiate this in 0, you can see here that dy dx equals minus x over y, right? So minus x over y. So that's generally true, right? So if you have some curve and you are looking at some quantity, which is the area for that point, namely its y value times its x value. So it's not the area under the curve, it's just the area of this box with that point at the corner. You maximize, if you like, you maximize that area in this way. So that's just a bit of calculus. And so in a similar way here, we want to choose x1 which maximalizes this area, because then we know that will give us the minimum total volume. And we've discovered that at that point the gradient is equal to the ratio, minus the ratio. But anyway, dy dx equals y over x. That's the point where we get the maximum area. And in fact, that tells us then exactly what we need to do. So the gradient at this point is nothing but the gradient of this curve at this point. And we know this curve, right? From our development here, we said we just put in our kinetics, and then that gives us an equation for our dependent variable. So we've got this function. We know this as a function of x. So we can just differentiate that function with respect to x and say, okay, if I'm applying maybe 0.35, then you can just use that in the function, and that will tell you that's the gradient there. Then you can, so let's say you've done that, so you know that gradient. And then if you look here, that's the gradient. So we want to know where's the x value where the gradient is equal to the ratio of these two. And in this case, you would then look at the height here. And remember, the moment you set an x1 value, that will prescribe this point. And we know that this is the final point, so that prescribes that point. So the moment you choose an x1 value, that prescribes the length of this line. And then, of course, in terms of this length, you've chosen x1, so that prescribes that length as well. So the ratio of these, right, this length divided by this length, that's in effect your y over your x. And so that's some number. And then you've also worked out the gradient. So the gradient of the curve at this point, you look for equality between the ratio of that to that. So this value divided by this value, that's some number. And then you ask, is that equal to this gradient here? And that's how you do this. And you don't need to to do anything else. You can just choose a set of points here and look for where that equality is the closest to being true. So if you pick a point here, for instance, you might get a flat gradient here, so a number close to 0, and then you'll get some other ratio here. Maybe that number is actually large. So you say, well, those two numbers are very far apart here. If I choose a point here, those numbers are somewhat closer together. If I choose another point here, oh, it's even closer. So you just try a couple of different values here, and then the value at which this ratio is the closest to the gradient, that's the point that gives you, that maximalizes this area and hence minimizes your total volume. Right, so I know this is a slightly more complicated case. There's a bit more work to do here, but that's how you can really minimize your total reactor volume. Right, so that's case 3, and that's the best in-principle reactor design to do. Now, we had talked about why we don't want to do infinite numbers of CSTRs. We said that the overhead costs of a reactor is going to make this infeasible. However, there's nothing to stop us doing it theoretically and commenting on the results. So let's for now suspend our practical concerns about the costs, and let's just say, let's go for it, and let's do an infinite number of CSTRs in series. Well, to begin with, so now we are not talking about minimizing total volume or anything like that. We are just going back to case 1 and saying, let's just take equal, or not case 1, case 2. Let's go back to case 2 and say, let's just take equal volume reactors and let's do our material balance. And we had said for n tanks in series, we get Ca in over 1 plus k tau to the power n. Right, so go back and look at that material balance. That's what we had for n identical CSTRs in series. Now, the space-time in each of those reactors is the volume in each one divided by the volumetric flow rate. And the volume in each one is going to be the total volume divided by the number of tanks, right? So V over N is VI. So that's tau. And now if you replace that in here, right? So here you've got k tau. If you replace tau for V over NQ, then let's see, you can say V over Q is actually tau 0, right? That's the space-time for the total setup. So the total volume over the total flow rate, we define that to be tau 0. But anyway, let's just say for now, that's the form that we have here. So as, or when you look at this, you can say that, look, we also have from mathematics, we have that the limit for n going to infinity for an equation of this form is the exponential. So look up in your first year maths, or it might even be your grade 10 maths, that as you, if you take 1 plus 1 over n raised to the power n, as you let n go to infinity, you get closer and closer to the exponential. So this is a known relationship from maths, okay? Now, if you go back here, so taking this simple mass balance, we've rewritten this tau as k over n times tau naught, right? So if you apply this relationship here, you are then able to say that this is nothing but Ca equals Ca in x of minus k over, minus k tau naught. Ca equals Ca in x of minus k tau naught. So do make the substitutions and have a look at that. So if this is true, then this is true. So we have now an equation that tells us the concentration for infinitely many CSTRs in series. So for infinite CSTRs in series, This is the concentration that comes out, and that's its expression. And if you have a look at your plug flow reactor, it's identical. In other words, if we take infinite numbers of CSTRs in series, we will get the exact same result as for a PFR. So that's not an expected result. So if we chug through the mechanics, the mathematical mechanics, you get the same answer, which you didn't expect, right? And in fact, it looks kind of impossible. So if you go and look at your design equation for a single CSTR, there's no exponential in there. We only have conversions, right? Look at exercise 1 for CSTR. There's no exponential involved. But now, as we use infinite CSTRs in series, we have this exponential that arises, and we possibly could not have predicted that this was going to happen. So what's going on here? Why is it that as we add more CSTRs in series, that we seem to be getting closer to PFR behavior? And if you go back to the concept, if you look at the pictures here, right, as we add more CSTRs in series, you are in effect creating a plug flow reactor. So you are creating, and remember, we are as we increase the number of CSTRs, you are cutting down the total volume into smaller and smaller pieces. So you may have started out with a 150 cubic meter reactor, then you made it 2, 3, 4. You went up to 50, so now you've got 51 cubic meter reactors, and you keep going. You're going to the thousands, hundreds of thousands. So you've got now infinitesimally small reactors in series, and each one is perfectly mixed. Imagine you've got 1 million CSTRs in series, and each one is a proper CSTR, so each one is perfectly mixed. Then what you see there is identical to a PFR. Right, a PFR has a plug. There's no interaction there's no mixing from one plug to the other. Yes, you have flow through, but you don't have molecules sort of diffusing across or anything like that. That's identical to what we have here. We have each one perfectly mixed, and there is flow from one to the other, but there's no diffusion across the wall or anything like that. So that is conceptually identical to the PFR behavior. And that is why the mathematical mechanics work out to give us the same solution. It's the same setup, right? Your infinitely many plugs, each one distinct, is identical to infinitely many CSTRs in series. Right, so that's why we get that. And even in your Levenspiel plots, right, as you can see, as you add more CSTRs, you get closer and closer to this line here. And so you get closer and closer to the result you get for the PFR. Okay, now that's all true. You could say, well, that's interesting mathematically. However, there's a practical outcome to this as well, which is that you are free to pick this value of n. And we had started out saying that we have these extrema. You have CSTR, perfect mixing. You have PFR, perfect not mixing. So you have these extrema, very hard to construct in the real world. And now you have this number n, which allows you to transition between the two. So you can say, well, for an n value of 5, I get behavior that's much closer to my real reactor. And so this is where we have started to generalize our development, and we are starting to think about how we can deal with the non-ideal cases. Right? So we are going to return to this point in the residence time distribution analysis, but you can start to see already that it is possible for us to use the ideal developments, our ideal theory, and start to describe the real world theory. Even though our ideal cases were physically hard to accomplish, right? Infinite amount of energy needed to perfectly mix this, almost impossible to get non-diffusion or deformation, right, to avoid laminar flow, impossible to maintain a plug, right? Now you have a number n that can be used to transition between these extrema. Okay, so we will return to that point. Then I would like you to work through in the notes in more detail this alternate case. So we have batch reactors, which by definition have no flow in or out of the reactor. However, you could consider that, well, why do I need to stick myself to this case where my reactant is going to run out? Right, so if you have one batch reactor and your species are just reacting away all the time, why can't we just add a stream that tries to restore the concentration of our reactant? So we could do what we call semi-batch operation. You can add one stream in, and you could keep feeding reactant in, and so you could maintain a good high reaction rate here. So you would get a good productivity and in fact a good reaction rate. So to develop the material balances, in this case then, we have to modify, let's take this case A and B. So B is the product forming and A is the reactant. So A is being consumed in the reaction. So the rate of formation here is negative, but A is also being fed in continuously to the reactor. And then component B is being formed by the reaction, so RB is a positive number. Right, and then if let's say the stoichiometry was like this, or the reaction kinetics were like this, then you could write a relationship between these two. So by looking at RA and RB, so if RA is probably RA is minus RB, then you could write it like this instead, and so you can establish a relationship between the two, and hence you can estimate the overall change in number of moles, and so you can do the overall mole balance and so on. So you can do all the expected things, and so rewrite your material balance in another form. So in the tutorial we'll work through some examples like this, and we'll look at how those concentrations vary in time and so on. Another thing you could do, which we would also call a semi-batch reactor, this time instead of feeding in only, let's say we also withdraw our product. So let's say we have components A and B in the liquid phase combining or reacting to give us component C, which is actually in the gas phase. And of course, as component C forms, if it was a pure batch case, component C would form up here and the pressure here would rise, and there may be safety concerns around this. So the pressure here rising versus the materials of construction, so that might be an issue. So you might want to remove component C. There might even be an issue that if it's a reversible reaction, then A could denature and go back to A and B, and A and B would rejoin the liquid phase here. So there are lots of good reasons to operate a semi-batch reactor where we just remove component C. So if we are constantly withdrawing component C, that reduces the likelihood it will return to A and B. So in this case, A and B are sitting in the batch mode here. But component C is leaving. So you can develop the balances here. In fact, I'm not convinced there's a change to these balances because these are in pure batch mode. And anyway, you can estimate then the overall conversion in this way. Right, so those are two simple cases that we'll look at in the tutorial. Then in terms of pressure drop, we had actually done this. So if you look at the previous section, we talked about the changes in volume expansion. So we had defined the volume expansion factor before. And in that case, we had assumed that the pressure was equal and the temperatures were equal. In this case, we are saying, well, if you've got a gas flowing through some tube or across some reactor, or even if it's a liquid flowing through a reactor, then due to resistance, due to collisions with wall and changing the direction of flow and so on, there is going to be a pressure drop. So instead of trying to claim that the pressure is always going to be equal, if you just accept that the ratio of those two things will result in a pressure ratio like this, then you could estimate the pressure drop, and for that you use your standard fluid mechanics type considerations and relationships. And so you estimate the pressure drop, and so compared with the inlet, you just update your pressure there, and then that helps you re-estimate your concentration. So this is basically saying if you have pressure drop across the reactor, you can simply account for it, and that will then influence your concentration in the reactor, and then that will influence your reaction rate. Right, so you can design even in the face of pressure drop. That's basically it. There are some comments here on selecting your reactors. A lot of this we've already said. So if it's a pharmaceuticals type application where you have grams of your product, and those are worth those are high value, then it's worth all the downtime between batches. So in a batch reactor, you deal with small amounts, but you can precisely control the conditions. And so you can get high purity products and highly controlled growth. And so a batch operation is suitable in a pharmaceuticals type application. And there you have to deal with unsteady operation and so on, which is something we will do. In a CSTR, if it's more like a commodities chemical and you want high volumes and high production rates, it's fairly easy to construct, but then we have to start thinking about networks and using a series of CSTRs in order to keep our capital costs down, in order to keep our total volume costs down. So that's the CSTR and what we have to think about when we use that. In the case of a PFR, it says it's lowest cost of production, but typically it means trying to have many tubes. But you can do it. Yes, you have sort of long, thin flows rather than short, fat reactors and so on. So it's a better use of volume than the CSTR. But it's hard to develop a model for the PFR, because quite often laminar flow will still play its role, diffusion will still play its role. So these reactors can be a bit harder to predict in terms of their actual delivery of product purity and so on. Okay, so among those three reactors, yes, we know how their volumes behave, what types of volumes are achievable in each case. We also know how to design around those to improve the types of capital costs that we'll get. And then we can also look at how to design for these alternate types of cases and how to develop the material balances there. So that's a fairly good grounding in this case of isothermal operation, where the temperature is fixed and constant. We have a full grasp of our material balances, and we can develop the volume, we can estimate the volume of the reactor. And so we have a good grounding in terms of actually starting to design our reaction processes.